Hello. After introducing the idea of semiconductors, its electronic structure, motion of electrons and holes in the semiconductor subject to an external electric field, and the concept of effective mass, now we will discuss about carrier concentration in semiconductors. We want the concentration of intrinsic carriers as a function of temperature in terms of the band gap. That's something we want to evaluate. We have already denoted the chemical potential as mu. This is the chemical potential for excitement of electrons to the conduction band at a given temperature T. In semiconductor physics, mu may be called the Fermi energy. At the temperature of interest, we may suppose for the conduction band of the semiconductor, if we have small temperature E minus mu, if this quantity is much greater than kBT, also large E, large energy epsilon and small temperature, for this kind of a situation we will have this satisfied. In semiconductor physics, mu is the Fermi energy because at the gap the Fermi energy sits, and in that kind of a situation that will be the chemical potential. Unlike metal, across the Fermi energy we don't have states available on both sides. Only one side we have states available, on the other side there is no state. Therefore, the energy associated with exchanging particles can't be different from the Fermi energy. It has to be the same as the Fermi energy. Now, in this kind of a condition, if this condition holds good, then we can write the Fermi-Dirac distribution function Fe nearly equals exponential of mu minus epsilon over kBT. How can we do that? This quantity, the numerator becomes very large, the denominator becomes small if this holds, and in that kind of a situation, sorry, this is not the numerator, the distribution actually is 1 over e power exponential of epsilon minus mu over kBT plus 1. This was the distribution, and this quantity becomes large, this exponential quantity, compared to 1. So we can ignore 1 here, and this, when taken in the numerator, becomes this, minus sign comes in the power. So that's the reason this expression is valid when this approximation is valid. So the Fermi-Dirac distribution reduces to this, and the probability that a conduction electron orbital is occupied, that in this approximation would be Fe much less than 1 of a conduction band to be occupied, but still there is finite probability of some carriers being present in the conduction band. So the energy of an electron in the conduction band would be given as epsilon k equals epsilon c plus h cross squared k squared over twice of the mass of the electron, me. This is assuming parabolic bands. What is epsilon c? This is the energy of the conduction band edge. Or the conduction band minimum. Now, if we replace me, that is mass of the electron, with the effective mass of the electron, then the above equation is valid even for non-free electrons. Otherwise, this equation looks pretty much like a free electron equation. This is the energy of a free electron. But if we put the effective mass here in place of the mass of the electron, then this equation will hold good even for electrons that are not free electrons. The corresponding density of states can be written as d epsilon is 1 over twice pi squared 2me over h cross squared power 3 over 2 times epsilon minus epsilon c, that is the energy in the conduction band, square root of this. The concentration of electrons in the conduction band would be given as n equals integration over the range EC to infinity, the density of electrons, electronic states times the Fermi function times the differential energy. This quantity calculates to be 1 over twice pi squared 2me over h cross squared power 3 over 2 exponential of mu over kb t integration from epsilon c to infinity epsilon minus epsilon c power half exponential of minus epsilon over kbt d epsilon, putting this expression of dE here, putting this expression of dE in this, we get this. Now, if we perform the integral, we would get n, the concentration of electrons in the conduction band, equals twice of me kbt over twice pi h cross squared over power 3 over 2 times exponential of mu minus epsilon c over kbt. The problem is solved for n if we know the value of mu. Otherwise, we cannot calculate the value of n. Now, it is useful to calculate the equilibrium concentration of holes. Let us call the concentration of holes P. The distribution function, Fermi-Dirac like distribution function for holes would be given, it would be related with the distribution function for electrons, and it would be given as Fh equals 1 minus Fe. Holes are basically missing electrons, therefore this kind of a distribution function is justified. And then we can write Fh, knowing the Fermi-Dirac distribution function, 1 minus 1 over exponential of epsilon minus mu over kBt plus 1. This can be rewritten as 1 over exponential of mu minus epsilon over kBt plus 1, which is nearly equal to exponential of epsilon minus mu over kBt, provided mu minus epsilon, this quantity here, is much greater than kBt. If the holes are near the top of the valence band, that's the region where we consider holes, because electrons are missing from there. So, the lack of electrons, they they behave as carriers, and they are the holes. So, they behave like a particle with effective mass mh. With this kind of an arrangement, the density of states for the holes can be given by dH, a function of epsilon, equals 1 over twice pi squared twice mh over h cross squared power 3 over 2 epsilon v minus epsilon power half. What is epsilon v? This quantity is the valence energy of the valence band edge. So, if we have a band structure of a semiconductor somewhat like this is the valence band edge energy EV, this is the conduction band edge energy epsilon C. Now, if we proceed just like the earlier, we can calculate the concentration of holes P equals, here the integral goes from minus infinity to the valence band edge or the conduction band edge, does not matter because there is no state in between. Let us put the same EC dH function of epsilon Fh, that is also a function of energy, times the differential energy. This quantity equals twice mh kBt over twice pi h cross squared power 3 over 2 times exponential of epsilon c minus mu over kBt. For the concentration of holes in the valence band, this is the expression we get, and the concentration of electrons times the concentration of holes, this quantity is always a constant. You can verify it. So, in the mathematical steps we have never considered any intrinsic carrier. So, it holds for also extrinsic, that is doped semiconductors. We did not anywhere assume intrinsic semiconductor, therefore, the same treatment carries for the doped semiconductor as well.